300 million subscribers, 94 billion hours of video in just 6 months. At peak, Netflix alone is roughly 15% of all internet traffic on Earth. So how do you design a system that streams high-definition video to that many people in nearly every country without it ever stuttering? Let's design Netflix from scratch, the way you would in a real system design interview. Requirements, trade-offs, the math, the architecture, the database, and the actual tools that make it real. First, always start by understanding the scale, because the scale is what forces every decision that follows. Netflix serves over 300 million paying subscribers across roughly 190 countries. People don't open it for a few seconds, they watch for hours. That single fact, enormous scale plus long, heavy video streams, is the entire design challenge. Get the scale wrong and nothing else matters. Step 1 in any design, clarify the functional requirements. What must the system actually do? A user signs up and picks a plan. They create profiles so a family shares one account. They browse and search a huge catalog of movies and shows. They get personalized recommendations on the home screen. They stream a title smoothly on any device. And they can pause on the TV and resume on their phone right where they left off. Notice we are deliberately scoping it. We are not building billing fraud detection or the content production studio today. Defining what you will not build is just as important. Step 2, and this is where senior engineers separate themselves, the non-functional requirements, the qualities the system must have. It must be highly available. Streaming going down is front-page news, so we target around 4 nines, about an hour of downtime a year. It must be low latency. Video should start in under a second or two and almost never rebuffer. It must scale horizontally to hundreds of millions of users and massive bandwidth. Stored content must be durable. We never lose the catalog, and the system is overwhelmingly read-heavy. Far more people watch and browse than ever upload anything. Every one of those goals forces a trade-off because you cannot have everything at once. Take the famous CAP theorem. When the network inevitably partitions, you must choose between consistency and availability. Netflix overwhelmingly chooses availability. If your continue watching marker is a few seconds stale, who cares? But the video must play. That means embracing eventual consistency for things like watch history. Because the workload is so read-heavy, we cache aggressively, accepting that a cache might be slightly behind the source of truth, and we trade some storage cost and precomputation to buy speed by encoding every title many times in advance. Speed for storage, availability over strict consistency. Those are the core bets. Now the part people fear, but it's just simple multiplication. The back of the envelope. Say 200 million of our users are active on a given day, each watching about 2 hours. That's 400 million hours of streaming every single day. Now bandwidth. Suppose 100 million streams are running at peak and an HD stream is about 5 megabits per second. Multiply it out and you get on the order of 500 terabits per second at peak. No single data center on the planet can push that. That one number alone tells us the video cannot come from the origin. It has to come from a content delivery network at the edge. Now storage. Say 100,000 titles, and each one, encoded into many resolutions and codecs, averages a couple of terabytes. That's hundreds of petabytes before we even replicate it around the world. So here is our scorecard, the numbers that will justify every later decision. 300 million plus subscribers, a 4 nines availability target, sub-second startup with rebuffering kept under a fraction of a percent. Over 500 terabits per second at peak served from the edge, hundreds of microservices behind the scenes, and a roughly 100-to-1 read-to-write ratio. Read heavy, latency sensitive, globally distributed. Keep those in mind as we draw the architecture. Here's the high-level design. Follow a single request. Your client, a TV, phone, or browser talks to an API gateway. Netflix built theirs called Zool. It handles routing, authentication, and rate limiting. Behind it sit hundreds of small, independent microservices, each owning one job: playback, user profiles, recommendations, search, billing. They find each other through service discovery, Eureka. These services read and write to a data layer, a hot cache called EVCache in front of databases like Cassandra and DynamoDB. But notice the crucial split. The control plane, deciding who you are and what you're allowed to watch, is completely separate from the data plane, the actual video bytes. The gateway hands your player a manifest and a token. The video itself comes from somewhere else entirely, much closer to you. And that somewhere else is the masterstroke. OpenConnect, Netflix's own content delivery network. Instead of making you pull video across the internet from a distant data center, Netflix ships physical appliances, basically servers packed with solid-state drives running FreeBSD and NGINX, and places them directly inside internet service providers and exchange points in your own city. During quiet overnight hours, it prepositions the titles it predicts will be popular onto those boxes. so by prime time, the bytes are already sitting one hop away from you. This is how OpenConnect serves 100% of Netflix video. The control plane runs in the AWS cloud. The heavy video traffic never touches it. But how does a movie become streamable in the first place? That's the ingestion and transcoding pipeline. A studio delivers one enormous pristine master file, often terabytes in size. Netflix chops it into chunks, then encodes those chunks in parallel across thousands of cloud machines. The output is a bitrate ladder. The same title at many resolutions and bitrates, from crisp 4K down to a tiny stream for a weak mobile signal, each in several codecs. Netflix even optimizes the encoding per title and per shot. All of it lands in Amazon S3, then gets distributed out to the OpenConnect appliances. Why a ladder? So your player can switch rungs in real time as your network changes. That is adaptive bitrate streaming, the reason your video dips to blurry for a second instead of freezing. Let's zoom into the low-level design. What actually happens the instant you press play? First, your player calls the playback service to start the title. Second, the system verifies your identity, your subscription, and your viewing rights and hands over a DRM license. Third, it fetches the streaming manifest, and because that's a hot read, it usually comes straight from EVCache in well under 10 milliseconds. Fourth, a steering service picks the closest healthy OpenConnect appliance for you. Fifth, your player starts pulling video chunks, and for every segment it measures your bandwidth and chooses the right rung of the ladder. And sixth, in the background, your player sends heartbeats. Those events flow through Kafka, and your resume position gets saved, so you can pick up later on another device. Now the other low-level flow, the one that keeps you watching. Recommendations. The naive idea is to run a machine learning model the moment you open the app. Far too slow. Instead, everything you do, every play, pause, and scroll is emitted as an event into Kafka. Stream processors like Flink handle the real-time signals, while Spark crunches huge batch jobs overnight to train the ranking models. The key move. The personalized rankings for your profile are computed ahead of time and stored in a cache. So when you open Netflix, the home screen just reads a ready-made list. The expensive intelligence happens offline, never on the critical path of your request. Time for the data model, the database schema. In a system at this scale, you do not design one giant relational database with sprawling joins. You design each table around a specific access pattern. A user's table for the account keyed by user at a profiles table, since one account has many profiles. A content table holding title metadata, genres, and pointers to the video assets. A viewing history table, and this is the important one. It's partitioned by profile id, so fetching your continue watching row is a single, lightning-fast lookup, never a scan. And a recommendations table that simply stores the precomputed ranked list per profile. Each table is denormalized and shaped for the one query it must answer instantly. And no single database can do all of that well, so Netflix uses Polyglot persistence. The right store for each job. Cassandra, a distributed wide-column store, holds massive write-friendly data like viewing history, replicated across regions for availability. EVCache, built on memcached, is the in-memory layer that absorbs the enormous read traffic in microseconds. DynamoDB and key-value stores hold metadata and configuration. Elasticsearch powers search across the catalog. And Amazon S3 is the durable home for the actual video files and analytics data. Different shapes of data, different stores, each chosen on purpose. So let's connect every layer to the real tools, the ones Netflix actually runs in production. At the edge, the Zool Gateway. For service discovery, Eureka with services built on Spring Boot. Caching is EVCache and Redis. Primary data lives in Cassandra, DynamoDB, CockroachDB, and MySQL. Search runs on Elasticsearch. The data pipelines are Kafka, Flink, Spark, and Iceberg. Video sits in S3 and ships through OpenConnect. Everything runs on AWS Compute with their tightest container platform. And to stay reliable at this scale, they lean on tools like the Atlas metric system, circuit breakers, and Chaos Monkey, which deliberately kills servers in production to prove the system survives. This is a real, battle-tested stack. So let's bring it all home. To design Netflix, you start from the scale, then nail the functional and non-functional requirements. You make the core bets, availability over strict consistency, and caching everything because the load is read-heavy. The math tells you the video must live at the edge, which gives you OpenConnect. You split the control plane from the data plane, transcode every title into an adaptive bitrate ladder, precompute recommendations off the critical path, and shape each table around the query it serves. That is the Netflix blueprint, and the real lesson of system design is simple. At scale, every good design is just a clear, deliberate series of trade-offs. Thanks for watching.